Good afternoon. Good afternoon, all. Is my voice is audible? Are you able to see the screen? Okay, mark your attendance using 3 parameters. So once again, good afternoon, all. So this is the video lecture on design and analysis of algorithms. We are currently discussing module 3 prims, module 3 greedy techniques. Under that, finding minimum spanning tree using prims algorithm. So we have gone with a prims algorithm. So this is the prims algorithm we have seen. So I will tell you the prims algorithm again. So before going for the input and output, so why you go with a prims algorithm? So prims algorithm is for constructing minimum spanning tree. So the input will be the connected, weighted connected graph. G is equal to V comma E. Output will be ET. What is ET? Edges of the tree. Okay, so edges of minimum spanning tree, we call it as ET. E is set of edges composing minimum spanning tree. So that's why you give it as ET. Okay, so for initially vertices will be V0. V0 means it will can be set of tree vertices can be initialized with any vertex. So minimum spanning tree edges will be null. So what you have to do, find the minimum edge. E is equal to V comma U. So V is the source vertex, U is the destination vertex. V to U, you are connecting using edge E such that V is in Vt and U is in V minus Vt. So V should, what you are considering V should be in Vt, and what you are taking U, it should be V minus Vt. Okay, so keep on adding all the vertices, keep on adding all the edges, so that we call it as Vt then Vt union U, Et then Et union E. So finally return Et. So this is the algorithm what you have to write. If they ask you in the exam, you have to write this algorithm. This is the prims algorithm. Okay, so now you come for the next part, analysis of efficiency. So how you are going to find the time complexity, that is worst case, average case, best case of this minimum spanning tree. Okay, so understand this particular words. It depends on data structure chosen. It depends on which data structure you choose. For a graph and for the priority queue whose vertex property priorities are distances to nearest tree vertices. If graph representation is weight matrix, so priority queue is implemented as a, so if graph representation, then you go with a weighted matrix. So next you go with a priority queue. One is for graph, the other one is for priority queue. So if you have taken data structure as graph, then you go with a weight matrix. So if you are chosen with a priority queue is implemented as an unordered array, the running time will be length of vertices, number of vertices square. Okay, so on each v minus 1 iterations, the array implementing the priority queue is traversed to find and delete the minimum and then to update. So keep this two in mind. So which data structure? For the graph, you use weighted matrix. For priority queue, it is implemented as unordered array. The running time will be theta of v square. Okay, so we can implement, now you see how you implement this using graph and priority queue. Okay, so two things you have to go through. One, analysis of efficiency using graph, efficiency using priority queue. So we can implement priority queue as a min heap. So you all familiar in min heap and max heap, I can remember. In data structure, we have gone with a minimum heap and maximum heap. So here also we can tell a min heap is a complete binary tree in which every element is less than or equal to its children. So if the root node is less than child node, we call it as a min heap. Okay, so we can implement the priority queue as a min heap. So when we call it as a min heap, is anybody condition for min heap? What is the condition? Yes, what is the condition for min heap? Answer in the chat box. Yes, anybody? So in a tree, we call it as a min heap. What is the condition for the min heap? So here I have tell min heap is complete binary tree in which every element is less than or equal to its children. So if root node has minimum value, okay. So root node or any other node, every element is less than or equal to children. So if it is less than or equal to children, we call it as min heap. So deletion of smallest element from and insertion of new element into min heap of size n or big of log n operation. So deletion of smallest element and insertion of new element into min heap so consumes a efficiency of log n operation. Okay, so if the graph is represented as adjacency list and priority queue is implemented, as I have already told, graph representation, it is weighted matrix. Priority queue, it's unordered array. So priority queue, we have taken min heap. So if graphs is represented as adjacency list and priority queue is implemented as min heap, then the running time is taken as E log V. So this is the time complexity what we can take. So time complexity for both graph as well as priority queue, it is taken as big O of E log V. Big O of E log V. So why running time is in big O of E log V? So the very important question. This question will be appearing each and every time. Why it is E log V? You have to tell like that. So algorithm performs V minus 1 deletions of smallest element and makes the length of E, that is number of edges verification, and possibly the change of elements priority in min heap of size not exceeding V. Each of those operation is big of log V. Okay, so therefore the running time is given as V minus 1 plus E log V. V minus 1 plus E log V. So that is equal to V minus 1 plus E. So that we take it as E log V as minus 1 is less than or equal to E. So this is the content what you have to write if you are taking running time is in E log V. Okay, so this is up to Prim's algorithm. So now you come for the next topic. So next topic is Kruskal algorithm. So Prince, you have finished. Now you come for the next algorithm, that is Kruskal algorithm. So it is also used to find minimum cost spanning tree. Okay. So come for the Kruskal algorithm. So algorithm constructs a MST. And anybody can tell abbreviate MST? What is abbreviate MST? So what we call MST? What do you mean by MST? Here they are telling the algorithm constructs an MST as. So abbreviate MST. What do you mean by MST? Algorithm constructs a minimum spanning tree. So MST means minimum spanning tree as an expanding sequence of subgraphs. Okay, so expanding sequence, there is no expanding sequence in prims. Here you can expand. So expanding sequence of subgraphs which are always acyclic but are not necessarily connected on the intermediate stages of the algorithm. So these are not necessarily connected, but in Prim's algorithm, one to one, there is point to point link between the nodes. But here, not necessarily connected on intermediate stages of the algorithm. So they are not connected on the intermediate stages. So come for the working of the Kruskal algorithm. So Kruskal algorithm working. So sorting the graph's edges in non-decreasing order of weights. So what we tell? So sorting the graph's edges in non-decreasing. So what do you mean by non-decreasing? Non-decreasing is nothing but increasing order of their weights. So sorting the graph edges in increasing, non-decreasing in the sense. So it is also called as increasing. So increasing order of the weights. Okay, then start with a empty subgraph. So it always starts with a empty subgraph. It scans the sorted list, adding the next edge on the list to current subgraph if such an inclusion does not create a cycle. So it should not form any cycle. So it scans the sorted list. First, initially, it will starting with empty subgraph that I will tell you. Okay, so it scans the sorted list, adding the next edge on the list to current subgraph. So if such inclusion does not create a cycle, and skipping the edge otherwise. So this is the working. Now you come for this particular thing. Okay, so this is moving like this. See the arrow mark how you are going to represent. So this is the tree you are having. Okay, so in that you have to traverse to all nodes and find which is the minimum one. Okay, so in all this, the entire graph, which is the minimum cost you are having. Can you tell what is the minimum cost in the graph? Which is the minimum cost you are having in the graph. There is no source, there is no destination like that. In Prims, this was source, this was destination. But here it is not the case. So which is the minimum cost you are having? Yes, tell me, which is the minimum cost you are having? So understand this carefully. So it's very, very important for the exam point of view. So in the entire diagram, don't go for source or destination or any other. Find the minimum cost you are having. So in the entire diagram, minimum cost is 0 to 1. So this is the path 1. So now you can see this is the minimum 1 what you are having. So now these two are visited. Okay, so after 1 and 2, which are the next you are having? So after 1, what is the next number? 2. So where the number 2 is there? So 2 is there here, 2 is there here. Okay, so either you can go with this one or you can go with this one. So now which nodes? After this, now I have taken these two nodes. Okay, so if you take this two, only one vertex is been added. But if you go here, two vertices are added. Okay, because the two are not been named. But here, when you go for this two as first, so you are going to like only one vertex is the newly added. But if you go in this line, you have two vertices newly added. So that's why first I will go with the two vertices added. So after this one, now I come with after this, now I come with this one. So here the two path, it is coming like this. Okay. So now from here to here to here, I am joining. Okay. So now 1 to 2, from here to here it is 1, from here to here it is connecting, so I have joined the two lines here. Okay, so this is there. After 1 2, next number is, you find the number 3. 3 is there? No, 3 is not there. You come for 4. So where the number 4 is there? 4 is here and 4 is here. Okay, so you are having twice. So first you can connect this one or you can connect this one. For now, you can see, you can add this two and you can also add this two. That's why you see 4 path is been connected here and next path is been connected here. Okay. So if you are connecting one path with another path, make sure it should not make cycle. So if you are connecting one path with another path, make sure it's not finding current making cycle. So 1 to 2 to 4 path. So here fourth path is been done and here this 4 is been done. So after 4, what is the next number you are finding? So connected paths, it is showing like this. After 4, you have the number 5. 5 is there? No. You have the number 6. 6 is there? Yes. So now you see the sixth path. So after this, now you see this is connected. These two are visited. This is visited. This is visited. This is visited. So sixth path is already you are not going to take because these two vertices are already in our visited. So all these two vertices are connected. So come for after 6, you are having 7. 7, these two nodes are already been visited. Now you come for 8. So after that, now you see here, you can see. So this is connected here. So for path like this is connected, connected, connected. So everything. So 8 is not connected because this is connected with this one. This is connected with this one. So finally, which is not connected? 9 is not connected. So this is the path what we take here to visit all the nodes. Okay, so in that, which is the minimum 9 we have taken. So now what is the cost you are having of the path? What is the cost now? So tell me what is the cost of this path? So first cost, first line 4 and next you have 8. So after 8 you come with 1, next you go with 2, next you go with 2 plus 4 plus 7 plus 9. So this is the cost you will be having. So what is the cost you are finding here? 2, 4, 8, 1, 2, next again 2, 4, 7, 9. So this is the, what is the cost you will be having? That is the minimum cost. Okay, so this is Kruskal example we have gone with. So after Kruskal example, now you come for the algorithm. Kruskal algorithm is not simpler because it has to check whether addition of new edge to the edges already could create a cycle. So it is not simpler because you need to check whether the edge addition of next edge to the cycle to vertices will form the cycle or not. So that is the main Kruskal algorithm. This is the example from the textbooks we have to take. So come with an example of the textbook. Okay, so tree edges sorted list illustration we have taken. So go with ascending vertices. Okay, so take this entire diagram. So number with 1, 2, 3, 4, 5, 6, 7 is not there, 8. So come with the linkage. So sort the things. Sorted list of edges you take. One is from B to C. Next is 2. 2 is from E to F. Come for 3, it is from A to B. Come for 4, BF, CF. Next, come for 5, AF, FD, AF, DF. Come for 6 like that. So now BC. So which is the smallest one? You add that one. So after BC, what is the next one you are having? Minimum one? EF. So EF is been, first you take EC. Okay, so first BC has been already taken. Now you go with EF because it is the next minimum one you are having. Next you go with 3. 3 is only one, that is AB. So AB has been connected here. Now you come for the after AB. Now you have 4, BF and CF. So in that, which one you are going to take? You are going to take BF here. Okay, so BF is finished. Now you come for CF. So CF already there, DF already there, DF you go with. So DF will mark 5. So DF of 5. Okay, so now you come for the algorithm. So Kruskal MSK algorithm. So this is the algorithm what we have taken. So Kruskal of graph G. So what is the name? Kruskal algorithm for constructing minimum spanning tree. Input weighted graph G is equal to V comma E. Output is ET, that is set of edges in non-decreasing order. So ET is set of edges of the minimum spanning tree. So this is the algorithm. Counter less than vertex minus 1, k is equal to k plus 1. If ET union EI is acyclic, then add ET is equal to ET union EIK. So finally written ET. So now you come for the analysis. Okay, so coming for analysis, the crucial check whether two vertices belong to same tree can be found out using union find algorithm. The efficiency of Kruskal algorithm is based on time needed for sorting the edges of the given graph. Within the efficiency of the within the efficient sorting algorithm, the time efficiency of the Kruskal is given as big of E log E. So there in prims it was E log V. So but here it is E log E. We are not going for any vertex. We are directly taking only the edges. So that is the analysis on Kruskal algorithm. So if they give you, you have to go through this particular thing. So you can ask me any questions. So why you have taken, you have after BF, you have directly gone with DF. Why not CF and AF? Because F is already visited here. Okay, so come for CF here. CF is not being taken. First one is BF. So BF is already taken. You have not taken CF here. So why you have not taken? C is already visited. F is already visited. Okay, now you come for AF. A is already visited. F is already visited. Because there is a link between that. So come for DF. F is visited, but D is not there. So that's why you mark the edge from DF. Okay. So now from DF5. So now you come after AE. So A is visited, E is visited, CD, C is visited, D is visited, DE, D is visited, E is visited. So there is, that's why we take DF of I as last one. So this is illustration of Kruskal algorithm, and this is Kruskal MST algorithm and analysis. So Prim's algorithm as well as Kruskal algorithm both will go with a time efficiency of of E log E. So Prim's we take E log V. So Kruskal will take E log E. So this is up to Kruskal algorithm. So have you understood? Yes. Have you understood? Yes, reply in the chat box. Okay. So all these particular video lectures will be uploaded in the YouTube channel link. So kindly go through the videos. You may find it difficult to understand, but go through YouTube videos and understand the concept clearly. Okay. So I hope you all got understood. So kindly like, share, subscribe for the channel and get the basic knowledge of the analysis of all the algorithms. Okay, so I will be ending this particular session. Meet you in the next upcoming class. So thank you all. Stay home, stay safe.